Hello everyone! So here we are in the fifth unit that we're talking about in Algebra 2, talking about factoring now again with polynomials. That's right, factoring is back, and it's bigger than ever. So one thing that you might find or need to find in your notes as we kind of go through some examples today is this factoring reference foldable that we made back in the Unit 4 when we first started talking about factoring. So that's just actually last chapter ago, but it was months ago really. And what does it mean to factor and why we use it is to help us solve or to find those solutions. So these methods are going to come back for us. We're going to continue to use them, but the problems are going to be a little bit more complicated. So please remember that to factor means to break apart into little parts that were multiplied. So the strategies that we're going to use are the same, but the answers and the problems look a little different now. And now that we're dealing with those higher order polynomials or more pieces, more terms, higher exponents, we're going to be using the same strategies, but our answers are going to look a little different. So this is the first one I need you to get in your notes. We're going to take another look at greatest common factoring. And if you don't want to write all the words, that's fine because you have that in your foldable. But it's when we look for a common thing you can take out of all the terms. So the reason we do greatest common factor first is because you should always ask yourself if there are any factors in common before doing any other type of factoring. So this is your number one go-to. This is the thing you always check first. It makes the problem easier if you do this first. So as I look at these two terms, I notice there's a 50 and a 25. So I would ask myself, what's a common number that I can divide out of both 50 and 25? The greatest number that I can divide out. And the answer to that is 25 itself. I can divide 25 by 25 and 50 by 25. I also look at these little x deals, and I need to take some x's out as well. They have x to the fourth x squared. That means I can factor out an x squared from both of them. Once I decide what it is I'm taking out, this is the greatest common factor, then I actually do the factoring. And that is I divide it out of each piece. So 50 divided by 25 is 2, x to the fourth, but I'm taking two of those little x's out, so x squared, he now becomes x squared left on the inside left. Okay, 25 divided by 25 is a minus 1. And x squared, but I divided those x squareds out, so he has no x squareds left. So this is what it looks like when it's factored. So these are the factors that multiply to make that. That would be my final answer at this point. Later on, we will continue and solve them, but for right now, again, we're just taking a look at the factors. Another way we factored was using group factoring. What you're going to notice now is we still have 4 terms, right? But some of the numbers get a little bigger and the exponents get a little bigger. So remember with group factoring, we go ahead and place them into 4 boxes because there are 4 terms. And 15 here. And we once again divide out of every row and column the greatest number and variable that can be divided out. So 30 and 18 can both be divided by 6, and they can both have an x squared taken from them, so 6x squared. This row, negative 25 and 15, can both be divided by 5s, but I think I'm going to take a negative 5 out here because that row starts negative. And now I'm going to go up like this, 30x to the third and negative 25x. Well, I take a 5 and an x out. And up this last column here, negative 18x squared and a 15, I'm going to take a 3, but I'm going to make that be a negative 3 since that column starts negative. And again, you can check by multiplying like you would do in science, okay, with the whole genetics deal, and you can check your answer and make sure it makes sense. But our two factors would be 5x minus 3 and 6x squared minus 5. So before we were getting like 5x minus 3, 6x plus 5 or something like that. Now we're going to see some higher exponents in our final answers. So we also then, after group factoring, talked about what if you have 3 pieces. So these are trinomials in quadratic form, it's called. So 3 pieces, we want to take a look at trying to get them to turn into 4 pieces to fit in the 4 squares. So we used the AC method, ladies and gentlemen. So AC method, one more time, is us taking A times C, negative 24. Okay, negative 12 times 2 is negative 24. What multiplies to make negative 24 and adds to make negative 5? Negative 8 Positive 3 will do that. So once I decide those are the little guys I'm going to use, then I stick them in the 4 boxes. The A and the C remain constant in our problem here, but we replace the negative 5x with these two guys over here that we said are the same thing as negative 5. So negative 8x and positive 3x. And we do the same thing we would do for group factoring or greatest common factor. I'm going to divide a 2x out of those two, divide a 3 out of those two. Going up, I'm going to take just an x out of those, and here a negative 4. So my two factors are x minus 4 and 2x plus 3. So those are my factors, and that would be my final answer if it said to factor. What you're going to notice on some of our higher level ones now is some of those powers are going to be a little different. Another example of this AC method. Take a look at this guy. Okay, remember we have higher exponents here. So one of the things we always want to do and remember to check is that greatest common factor idea. So the first thing I'm going to do is take out a greatest common factor because there is one. 4, negative 20, 24, they can all be divided by the number 4. So the first thing I'm going to do is take out a 4 as well as some x's from each of those. I'm going to take out an x squared since they all have enough. They can give me that. And see what this problem looks like after I do that. So if I take it out of the first term, 4 divided by 4 is 1, x to the 6th, but I'm dividing out an x squared. That would leave me with x to the 4th left. 6 minus 2 is 4. Negative 20 divided by 4 is negative 5, and he'd have x squared left. And then 24 divided by 4 is 6. He had x squared, but I'm taking him out, so he doesn't have any x's left. So first thing I did is greatest common factor. Now, we're not done. Just because we do one thing doesn't mean it's completely factored. This guy still has 3 terms, and that's still a trinomial that could be factored. So we still need to take a look at how we just factor that piece. Now, because he's a trinomial and he has 3 pieces, we want to turn him into 4 pieces. We're going to do the AC method. Now, the A and the C, don't worry about this guy out here. He's the greatest common factor. The A and the C are 1 and 6. So what multiplies to make 6, if I multiply 1 times 6, and adds to make negative 5? Remember, it could be negative 6, negative 1, or positive 6, positive 1, or 2, 3, or negative 2 and negative 3, since 2 negatives multiply to make a positive. We're looking for the ones that add to make negative 5. Once I decide which partnership or which pair I'm going to use, then only this trinomial here, this little guy here, goes in the 4 squares. X to the 4th minus 2x minus 3x. I'm taking those from our list over there. And then the 6 was the C value. So now we're going to take out something greatest, or we're going to take out things rows and columns, but I'm noticing I'm not quite done here. Remember that this was negative 5x squared? These have to be x squareds then, not just x's. Sometimes we're used to having an x there. You saw me just do it right there, but I forgot that those have to be x squareds. So I'm going to place the x squareds there in those middle boxes since my original problem had an x squared in the middle. So now let's do rows and columns. I'm going to take out here, just an x squared can come out of those 2 terms. These guys can be divided by negative 3. Going up here, what can I divide out of those 2? X squared. What can I divide out of those 2? Negative 2. Okay, so now our factors are x squared minus 2, x squared minus 3, and then don't forget that we've kind of ignored to this point this 4x squared. He's a part of the problem's factors. He needs to be listed as well. These are all of the factors that I would need to distribute in order to get my original problem back the way he started. So this idea of using greatest common factor to get it started and then continuing until we have him completely factored is what we want to keep doing and keep practicing now as we go. Okay. Let's take a look at some perfect squares. We also talked about difference of perfect squares. This is another example of that. So when you use the difference of perfect squares pattern, you're looking for perfect squares. That's what these two numbers are. And then the fact that there has to be a subtract sign there in order to use that pattern. So because I have 16 and an 81, I know that I can jump right to the factors. What is it that multiplies to make 16? Well, that'd be 4 and 4, because the square root of 16 is 4. Now notice I needed an x to the fourth right here. So putting an x and putting an x is not going to make me have an x to the fourth. I need to do x squareds here. Okay, x squared times x squared would make an x to the fourth. Now let's look at that 81 in the back. 81 is 9 times 9, 1 positive, 1 negative. Okay, so far so good. Now if I look at what we have so far, this one looks pretty good, but I'm noticing this guy right here is still a difference of perfect squares. 4 and 9 are both perfect square numbers. That means I can split him apart one more time. To make 4x squared is 2x times 2x. To make 9 is 3 times 3, 1 positive, 1 negative. And that first one is not a difference of perfect squares, so we can leave him as is because he does not follow the difference of perfect squares pattern. So all of these are the factors that would need to be multiplied in order to create this original problem. Okay, so we're talking about factoring and factoring completely now in this unit. One of the things that comes up is, what if the number's not a perfect square, but it's a perfect cube? So sometimes people need to start recognizing what numbers are in fact perfect cubes. So in your notes, go ahead and start making a list like this. Go ahead and use a calculator to complete these to find out what numbers are perfect cubes. 1 to the third power is 1. 2 to the third power is the same thing as 2 times 2 times 2. That's 8. 3 to the third power is 3 times 3 times 3. That's 27, and so on. Continue this list. This one is 64. This one is 125. You go ahead and complete the rest of these, and we're going to need these perfect cubes as we go ahead and factor the next part. So go ahead and take a minute and fill out the rest of those in your notes, and I'm just going to go on to the next slide, so you might want to pause the video now. So when you look to factor things, like the difference of perfect squares was pretty easy because you knew square rootable numbers. Now what if we have perfect cubes, those numbers that you just made a list about? The sum of two cubes is a thing that we want to look for, a pattern that we're going to use to help us factor. And this is new to us. We did not do this in Unit 4. So what we're looking for in words, we're going to look for two things that are added together and both have a cube root, or both are from your perfect cube list that you just made. So this is kind of weird, but this is the way it's written in your book. This is what the problem looks like. And then this would be how we factor it. So if the problem looks like that, this is how we're going to go ahead and factor it. So when I look at this first problem, I have x to the third plus 64. We want to make sure the problem follows this sort of format. Well, I'm seeing that the x is pretty much like the a there, but I'm noticing that 64 doesn't have a little cube on him. We want to turn that 64 into something to the third power. So we can keep it as x to the third and then plus something to the third. Well, what is that something to the third power that would make 64? If you look back on your list of perfect cubes, notice 64 is the same thing as 4 to the third power. So we're basically going to rewrite the problem so that we have something to the third and something else to the third. 64 is the same thing as 4 to the third, but we're just rewriting him in a way that I can say what the A is and what the B represents. According to this formula that has A's and B's in it and kind of helps lay out how we're going to factor, we want to identify what part of the problem represents the A and what part represents the B. So the A is the number here with the x to the third. A is going to be an x, and B is going to be a 4. So everywhere up here in this how do we factor it pattern, we're going to replace every A with an X and every B with a 4. So it's going to look like X plus 4, because that's the A and the B. Then it says do the A thing squared. Well, the A thing was an X, so I'm just going to write X squared. Then put a minus sign. Then take the A thing and the B thing and multiply them. A thing and B thing are x and 4. If I multiply it, it becomes 4x. Then put a plus sign. Then do the B thing, which is a 4, squared. So that'd be 16. So this is saying when the problem looks like this, these are the factors. It is factored. If I follow the pattern, I don't have to do any, long work of putting it into squares or any other strategy, rather than follow that pattern to help us break it apart into little pieces we could solve later when the time comes. So it's just using a pattern to help us break it apart. Now the same sort of thing happens when you have a difference of two cubes. You're going to want to write this one down. Here's a new pattern. What if there's a subtract sign in between our little perfect cube guys? Well, again, this is what the problem looks like. And then this is how do I factor it? Okay, how do I factor it? So go ahead and we're going to take a look at this 8w to the third minus 27. Now, if you think about perfect cubes, again, back a couple slides here, I'm noticing that 8 is a perfect cube. Okay, that's a big deal. And I'm also noticing that 27 is a perfect cube. So remember, 8 is the same thing as 2 cubed. So if I was going to rewrite this, I would say this is 2w cubed. Okay, the 2 is cubed turns into the 8, the w cubed turns into the w cubed, or to the third power. So I'm rewriting it so I can see what it serves as the A and what part plays the B. Okay, the subtract sign, 27 is the same thing as 3 to the third power. So when it's rewritten so I can see who's the A and who's the B, I can't just use 27 and 8. It says something has to be to the third power and something else has to be to the third power. And I didn't have that originally. So now I do. I know that my A is going to be 2w, and I know that my B is going to be the 3. So everywhere in this pattern, how do I factor it? I'm going to replace every A and every B with those things. So my factors are going to look like one little parenthesis, one big parenthesis here. The A thing, the formula says, okay, so 2w, minus the B thing, okay, 3. And then the A thing squared. The A thing is 2w. That means you got to square both parts. So squaring the 2 and squaring the w turns it into 4w squared. Then the plus sign. Then the A times the B. Well, that's 2w times 3. Well, that'd be 6w. And then plus sign, and then the B thing squared. The B thing was 3, so that's 9. There we go. He is factored. I didn't have to do any special calculations. I don't have to find a greatest common factor. I don't have to do anything like that. This is the final factored answer. Okay, so those cube patterns are new to us. They're brand new. We did not have them in our original notes. So just kind of overview. Remember that you need to know about the greatest common factor. Take that out first, and then we look for those other methods we can use to factor, and our end goal is to always factor completely, all the way down. Okay, completely, factor completely, okay? Factor completely all the way down. Do not stop. Okay, keep going until you cannot break it apart anymore. So we're going to take a look at how all of these things play together tomorrow. Thanks.